Lesson 1-6, Solving Compound and Absolute Value Inequalities. Today is part 2 of this lesson, so we're going to work on objective number 2, Solving Absolute Value Inequalities. To review from part 1, compound inequalities are two inequalities put together with the word and or the word or. And means the intersection of two inequalities, or means the union of two inequalities. When we're solving absolute value inequalities, you can rewrite them using a compound inequality. So if you look at number 1, if the absolute value of A is less than B, then we have an intersection where A is in between negative B and positive B. Number 2, if the absolute value of A is greater than B, then we have a union. A is greater than B, or A is less than negative B. Here's an example. In letter A, we have the absolute value of A is less than 4. This is an example of an intersection. If you go back to number 1 on the last slide, we can rewrite this by saying that A is in between negative 4, meaning A is greater than negative 4, and A is less than positive 4. So if you see the less than symbol in your problem, you're going to rewrite it like this, getting rid of the absolute value bars. So our solutions are in between negative 4 and positive 4. When you graph it on the number line, it looks like this. Here's negative 4. Here's positive 4. On each endpoint, we're going to use an open circle. And A is in between these two values, and so our solution region is anything in between. Okay, not including negative 4 or positive 4, but anything in between those two numbers. If you wanted to check a value, you could certainly test one. Like if you wanted to test, let's say negative 2. Plug it into the original problem, and you'll be able to check that your solution region works. The absolute value of negative 2, which is 2, is less than 4. That's a true statement. Let's try letter B. If you see the problem written this way, I highly suggest that you rewrite it, putting the variable first. So the absolute value of D is less than 3 would be the way to rewrite it. Now you can see that we've got a less than situation. We've got an intersection. So to rewrite it to get your solutions, we know that D is going to be in between negative 3 and positive 3. Graph it on the number line. Negative 3, positive 3, and again we use open dots because the symbols are strictly less than, and our shading goes in between those two values. You use the same thing if you have a less than or equal to, you just would color in your circles, but you would use the same formula. We have intersections here. Let's try these. The difference with these problems is we have greater than signs, and so actually we need to follow formula number 2 on the formula sheet a couple slides ago. In letter A, we've got the absolute value of A is greater than 4. Well, that tells us that A could be greater than 4. This is kind of our case 1. Or A could be less than negative 4. If you need to go back and follow the formulas from a couple slides ago, go ahead and do that. We've got a union this time of the two inequalities. Let's take a look at what the graph looks like. Here's negative 4. Here's positive 4. The symbols tell us to use open circles. A is less than negative 4 means anything to the left of negative 4. Or A could be greater than positive 4, so open circle on positive 4 shaded to the right. And you can see that we've got a union of two graphs here. In letter B, the absolute value of X is greater than or equal to 3. The greater than sign tells you that we've got a union, so X could be greater than or equal to 3. Or X could be less than or equal to negative 3. Just like when we were solving absolute value equations, we kind of have a positive case and a negative case. Also notice though that you're not just switching the number to be negative, you're switching the inequality sign as well. Let's take a look at the graph. Here's negative 3. We're going to use a closed dot on negative 3. Because of the symbol, it has an equal to sign underneath. This says x is less than or equal to negative 3. Less than means shade to the left. Over here is positive 3. This first inequality says x is greater than or equal to positive 3, so closed dot there, shaded to the right. Let's try one that's a little more challenging. Okay, so the first thing I would do is I would look at my symbol. Okay, I've got a greater than sign here. That means I'm solving a union of two inequalities. Case 1, 3x minus 12 is greater than or equal to 6. Basically the original problem. Case 2, 3x minus 12. Now, this is our negative case, so we're going to reverse the sign is less than or equal to negative 6. You're reversing the symbol and the number on the right side here. Let's go ahead and solve each case to get the two-part solution. Alright, so over in case 1, I'm going to add 12 on each side, and we get 3x is greater than or equal to 18. Divide both sides by 3. And for the first part, we get x is greater than or equal to 6. Case 2, remember the difference here is our sign is less than or equal to, and we've got a negative 6. I'm going to add 12 on both sides. And we get 3x is less than or equal to positive 6. Divide both sides by 3. And we get x is less than or equal to 2. Okay, now remember that we expected this to be a union of two graphs. So it's one or the other. Okay, we're using the word or here. One or the other. So when you draw your graph, we've got 2 and 6 as the critical values here. X is less than or equal to 2. I can use a closed dot there, shade to the left. And x is greater than or equal to 6. So I'm going to use a closed dot and shade to the right. Okay, and again, if you wanted to check a solution here, pick something that's in your solution region, like maybe try 7, plug it in for x, and check to make sure that the inequality is true. Okay, let's do one more here. The absolute value of 3x plus 4 is less than 10. Less than tells me that I'm going to have an intersection here. If you wanted to, you could set up a case 1 or case 2, or we can take what's inside the absolute value sign and kind of sandwich it in the middle between our positive and negative numbers. It'll look like this. 3x plus 4 is less than 10, or we could say 3x plus 4 is greater than negative 10, but here's an easy way to write it. Put 3x plus 4 in the middle and your two endpoints, negative 10 and positive 10. You're really solving case 1 and case 2, but you can do it all in one problem here. Okay, so I'm going to subtract 4 from the middle and from each endpoint. That gives me negative 14 is less than 3x is less than 6. Okay, now we're going to divide everything by 3, again in the middle and then on each endpoint. The goal here is to get x by itself in the middle of our two symbols. And we have negative 14 thirds. If you want to convert this into a mixed number, you certainly could do that. I would do it so that you can tell where to graph it on the number line. So 3 goes into 14 4 times. That's our whole number, so we've got negative 4. 3 times 4 is 12. That leaves us with 2/3 left over. So negative 4 and 2/3 is less than x, and x is less than 6 divided by 3 gives us 2. Okay, now you graph your solutions on the number line. The two values we want to include on our number line is negative 4 and 2/3 and positive 2. Now, the symbols here tell us to use open dots, and you can read this by saying x is in between negative 4 and 2/3 and 2, not including those endpoints, so we're going to use open circles there. Okay, and that would be the graph of the solution region. Okay, let's try one word problem. According to a recent survey, the average monthly rent for a one-bedroom apartment in the city is $750. However, the actual rent for any given one-bedroom apartment in the area may vary as much as $250 from the average. Write an absolute value inequality to describe this situation. Well, we know that the average rent is $750, and it's going to vary about $250 from that number. So we need to define a variable here. Let's say that x represents what the actual rent could be. Our absolute value inequality needs to look like this. The absolute value of the actual amount x minus $750. So we're saying the difference in the actual amount and the average in the absolute value bars has to be within $250. So we're going to use the less than or equal to sign and put 250 over here. That's our absolute value inequality. Now, when you solve this, you could either solve this inequality or you can just add or subtract 250 from 750. Let me explain. If 750 is the average and we have to be within 250, on the low end, we could get rent for $500. And on the high end, we could get rent for $1,000. That would be $250 from 750. Those will be the range of values. Okay, and you're going to get exactly those numbers if you solve the inequality that we wrote in Part A. All right, finally, please try these two problems for class tomorrow. We'll go over the answers so that we could check if you really understood this lesson.